How does that work for you?
It's coming, and it's perfect. It's on full screen. So please start whenever you want. It will be 25 minutes starting from now. So I'll give you a 5-minute warning.
Perfect.
Thank you.
Well, first of all, if Marco is present, then happy birthday. I'm one of those colleagues whose early research was strongly influenced by your work. And I think my first paper in financial maths was on calibration of option pricing models. And we were reading some of Marco's papers very carefully. And I really liked the optimization angle that he had there. And thank you for the other organizers too. I think I'm mostly grateful for Marco for organizing this series. I've enjoyed my every visit to Rio. It has been really a lot of fun, a lot of scientific discussions, and I could say life-changing. One of my, well, I can honestly say it's my favorite conference series on the planet. I hope we'll get to continue with the physical version soon. So the talk, I'm giving a talk. It's going to be very superficial in many aspects. I'm going to talk about this book project that I have with Ari-Pekka Perkki. We've been working on this for more than 10 years now. We published several papers on the topic. And I try to give a quick overview of what we plan to include in the book. You can see this rough outline on the left. So I will be talking about convex stochastic optimization, CSO. That will be the first part of my talk. And then I hope to get to the end of dynamic programming section. I doubt I have any time to say anything about the duality. I've spoken about duality in convex optimizations, convex stochastic optimization in Rio meetings previously, I think some 7-8 years ago. I don't think I talked about dynamic programming. So it's, of course, very old classical topic, many works on it. What we are doing here is trying to lift that classical theory of dynamic programming, dynamic stochastic programming, to a new, more general class of problems that has many interesting applications in finance, operations, research, and many other fields. So much of the motivation that we had indeed comes from financial maths. We are looking at the general class of stochastic optimization problems that covers all classical financial problems and also allows to include portfolio constraints, transaction cost, illiquidity effects, and many other features in a single shot. So the general theory will cover all of those as special cases. We'll also cover things like convex stochastic control, which is in itself, it's a big topic. Often, well, as many of you know who has worked on stochastic control, it's often not very closely related to convex optimization. But what we are doing here is we're trying to draw connections between the two fields. And indeed, there are so many very interesting links between those two fields. And also, it allows to use techniques from another field in the other one, and they sort of support each other. That's what the title of the book, the subtitle here, is trying to convey. And of course, we'll also cover those classical models coming from operations research. And what we do mathematically, it's a combination of classical convex analysis, these functional analytic techniques that have been developed for general classes of convex optimization problems. We go a little bit beyond in order to cover financial problems. We use some tricks and theories from stochastic analysis, Converse theorem, and so forth, that replace classical compactness arguments. With this combination, we are able to get to the goal. We cover most results in dynamic programming, in financial maths, operations research, and also same can be said about the duality part. And those two parts are nicely intertwined together. What we also aim to do is to, by this abstractification, you throw away many of the unnecessary details that may obstruct the presentation of the theory. So one can see this as simplification of those classical theories. So we simplify, unify, and extend existing theories. For example, in financial maths, like I mentioned already, we can include those market imperfections, also different kinds of trading strategies like these semi-static trading strategies that are important, for example, in this martingale-optimal transport, including those entropic versions of them. This time, of course, we are looking at, since we talk about stochastic optimization, we do have a model-dependent optimization problem. So there will be a reference probability measures. We are more in the classical setting of stochastic optimization. And one of the major simplifications that we've done is we employ the theory of normal integrants, the theory of random set-valued mappings developed back in the 60s and early 70s. And that allows us to resolve many of the problematic measurability issues that come up in other approaches to stochastic dynamic programming. The duality part, as one might guess, gives optimality conditions and dual problems like duality usually does in the context of optimization. So like I said, I divided the presentation in 3 parts. I start simply by trying to outline the problem, trying to give the impression that it indeed is a very general framework to look at these optimization problems. So one could say that the convex stochastic optimization goes back to the works of George Dantzig. Soon after he developed the simplex algorithm for linear programming, he realized that many practical problems have these stochastic components that should be taken into account. Not listed here is Kantorowicz, who was sort of the Russian counterpart. He also, like we've seen, for example, in the optimal transport context, he was a big early contributor to linear programming and operations research. There's also Beal, often contributed as one of the fathers of stochastic optimization. He, like Dantzig, looked at linear stochastic optimization problems. And also from the same origin, from OR, comes Richard Bellman, who developed the dynamic programming principle. But that, like I mentioned, has largely been developed in a different direction since the early times. And nowadays, when you read papers or books on dynamic programming, you don't see many connections between these classical convex optimization-based works in operations research. About the theory, we'll be heavily relying on the notion of convex normal integrants, and that's a very useful notion in probability variational analysis developed by Rockefeller and many contemporaries back in the 60s and 70s. There's a long series of papers by Rockefeller and Weitz from the 70s where they used that theory to develop basic theories for convex stochastic optimization in discrete time. I mentioned the book by Bertsegas and Shreve. They take a different angle. I come back to this because there's some interesting debates and links between the 2 strands of research. We'll also need to, in order to cover financial models, we need to extend works of Rockefeller and Weitz because they studied essentially bounded decision strategies, and their problems usually had uniformly compact decision sets. And of course, these classical financial models go beyond that, where typically your strategies are not even in a locally convex space. You look at general measurable decision strategies, and there's no compactness there. So we aim to cover all of those. Here's the problem. So we are going to look at, over a filter probability space, adapted decision strategies. X, N stands for adapted strategies. At each time you choose a vector, the dimensions may vary at different points in time. Adapted sequence of decisions that minimizes the expectation of some convex functional. So we're looking at this kind of convex integral functionals. This function h here depends on the whole path of your decisions. It also may depend on the omega, so it's a random lower semi-continuous convex function, and then you integrate with respect to some given reference measure p. And h being a normal integrand means that as a function of the decision strategy, so n here denotes the whole dimension of the path. So as a function of the path, the function h is convex and lower semi-continuous, and then it's jointly measurable with respect to the Borel sigma algebra on the path space and the sigma algebra f on the probability space. And important here is that h is allowed to be an extended real-valued function. So that allows us to incorporate many different kinds of constraints into this compact formulation with a single objective. Then some examples. The first one, not sure if it's very interesting for math finance people. This is just a link to those classical OR models. If you look at the linear case, you get back the Danzig's stochastic LP model. This is a format that Rockefeller and Wetz studied back in the 70s in several papers. Here's another simple one. It's the classical optimal stopping problem in discrete time. If you look at the second display formula here, we're trying to minimize over x. There's a constraint that all x's have to be positive. That's what this plus stands here for. And the total sum of the exercises, you may think of xt as a fractional exercise. That has to be at most 1. And then you have this reward process z, and you're trying to maximize or minimize the expected reward x times z. If x is a pure jump process, so that it only takes values 0 or 1, it's exactly the classical optimal stopping problem. So you may think of this as a relaxed stopping problem, and this is actually the most direct way to prove existence to optimal stopping, and works in continuous time as well. And the same kind of thing has been studied by Bismuth back in the 70s. And I think his results still are the most general ones on existence of optimal stopping. The optimal investment. So again, if you look at the second display equation here, we're minimizing over adaptive trading strategies. You have some claim to hedge. U is the claim. Then you can hedge that with the wealth, terminal wealth of your trading strategy. So you have this usual stochastic integral with respect to the price process S. You have some utility function or a loss function, and you minimize the expected loss. That has been studied by many colleagues, often in continuous time. There's a beautiful paper by Rasonen and Stettner from 2005 where they looked at exactly this problem. And again, that fits the general framework with the above choice of the normal integrand. And I should have mentioned that this property of being a normal integrand is a very robust one. It's preserved under many kinds of algebraic operations, and that's why it pops up so naturally in practical applications. And it's indeed a very, very general concept. You can extend the previous model to illiquid markets, and we've studied these kind of models in several papers by myself and together with with Ari-Pekka. The 2 papers at the bottom were published in Finance and Stochastics a couple of years ago. So this is essentially just extends the previous classical trading problem, utility maximization problem, by allowing for portfolio constraints, nonlinear trading costs, without assuming necessarily the existence of a numeraire or a cash account. the previous model comes out as a simple special case of this. Then the stochastic control. This is a convex instance. Again, if you look at the second display formula, we have the classical linear system equations here. A and B may be some random system matrices. U, capital U is your control, X is the state, lowercase u is the random noise. And then you're trying to minimize some expected loss. The loss functions may depend on the state as well as the control. You're trying to optimize over adapted states and controls. And here we found an interesting remark from the classical book of Persigas and Shreve. Like I mentioned, they do take a very different approach. They don't employ the theory of normal integrants or random convex sets in their study. More than half of their book is concerned with tedious measurability issues that come up in the dynamic programming recursion in discrete time. Their book is also on discrete time. And then we found this quote there. They were clearly aware of works of Rockefeller and Wetz and other people in OR using this kind of normal integrand approach, but they seem to have misunderstood something. They say here that the model of Rockefeller and Wetz does not include a special case with many important problems, such as, for example, the classical linear quadratic stochastic control problem. But that must be a misunderstanding, since this above model here, it doesn't only include linear quadratic control, but any convex control models. This function L here is any lower semi-continuous convex random function. It doesn't have to be real valued. It may take infinite values, so you can even include constraints on controls or the states or both. And like I said, their book spends a long time on working through those measurability issues. With the approach we've taken using convex normal integrands, these issues are resolved very, very easily. And we get under convexity and lower semi-continuity much more general models than they did. I'm conscious of time. I'm trying to, I guess I have some 10 minutes. So I'm trying to give a flavor of what we did in the dynamic programming. Like I predicted correctly, it seems I have no time to look into duality. So here we follow the classical Bellman recursion in finite discrete time. Rockefeller and Wetz did a beautiful generalization to stochastic dynamic optimization problems. There's a beautiful paper also from the same year by Igor Evstignev, where he essentially did exactly the same thing, but without assuming convexity. Both works did, however, assume that the feasible domain is uniformly bounded, so that all strategies were essentially bounded. Another difference between Rockefeller and Wetz versus Evstignev is that Evstignev quite elegantly used the notion of a conditional expectation of a normal integrand that he developed with his supervisor Dinking. There's a beautiful paper by Jean-Michel Bismuth. It was the first paper published after his PhD thesis, which studied convex stochastic optimization using normal integrands. He also understood the importance of conditional expectation of a normal integrand, and indeed his first paper was exactly on this topic. So that's what we will use. We found it very useful and flexible tool to develop the dynamic programming recursion. And here's the definition. The first two bullet points simply point out that the correct definition of a conditional expectation of a random variable in the case of potentially non-integrable and extended real-valued random variables. So given a normal integrand H, the G conditional expectation of the normal integrand is the normal integrand which is G measurable and satisfies this equation for any G measurable strategy or decision variable x. I know it's, if you haven't seen it before, probably looks very exotic thing. It's just going from an f measurable normal integrand to g measurable normal integrand, so that those expectations, conditional expectations, coincide for g measurable decision variables. In the case of a linear normal integrand, so here you have some random vector v, and your normal integrand is simply a linear functional with that slope. In that case, the conditional expectation is exactly what you would expect. You simply take the conditional expectation of your random slope v. There are many calculus rules, so this conditional expectation is a fairly robust property. If you know how to compute that in simple cases, then you will know how to compute that in more convoluted cases constructed by algebraic operations. So here's the basic dynamic programming recursion. So if you remember the original problem, we tried to minimize the expectation of this function age. We tried to minimize that integral functional over adapted strategies. The dynamic programming recursion reduces that to stage-wise and omega-wise minimizations. Just like in more specialized setups in stochastic optimal control. So you start with the original function, normal integrand age. You initialize your recursion to that. You take a conditional expectation of that functional, and then you minimize with respect to the last component of your decision strategy. And you can do it omega-wise since you did this conditional expectation here. And then you simply repeat the second, the steps 2 and 3 in this recursion until you get to the beginning. And here, to justify this, you need to prove that it's well defined, and that's exactly where the theory of normal integrands comes in. And that can be done in a very, very general way. This is exactly the same recursion that Evstignev and Rockefeller and Wett studied in the 70s, but we've dropped now all the compactness assumptions, and that allows us to go much further in applications to financial maths, for example. And here's one reason why the dynamic programming recursion is indeed interesting. It gives an optimality condition. It says that an adaptive strategy x bar is optimal in the original stochastic optimization problem if and only if you get this point-wise minimization condition with respect to these Bellman recursion functions. Here's a remark to some of you who may have studied papers by Rasonen and Stetter and others. People who don't work with normal integrands, they often go through this essential infimum, and essentially gives you the same thing, but I'd say with reduced simplicity. So going back to the classical results in the 60s and 70s on normal integrands allows you to get far simpler formulas and simpler derivations and theories. The second main theorem here about the dynamic programming is to prove the existence of the solution to the Bellman equation. Let me just remind you, this is the Bellman recursion. It's not a priori clear whether there exists such a sequence of functions ht that satisfies this recursion. The first theorem that I just showed assumes that one exists, and then it proves that you can indeed characterize optimal solutions using those solutions to the Bellman equation. And now the second theorem gives sufficient conditions for existence of a solution to this generalized Bellman equation. We assume here that the H is a convex normal integrand. We assume for simplicity now that it's bounded from below. That can be dropped, that can be extended. And we assume this algebraic condition, which looks at the lower level sets of the so-called recession function of H, and requires this set has to be linear. is a very general condition which, if you go back to the classical models in financial maths with illiquid market models, this condition here is exactly the no arbitrage condition on the financial market.
So Teemu, no more than 5 minutes.
All right, that should be enough. And just to be more explicit, here's the definition of this recession function that is involved in this condition. It's another convex normal integrand. Just notice there's a typo. There should be omegas throughout on the right-hand side. So you define this function pointwise for every x and every omega. And this limit exists because of convexity. This difference quotient here is monotonically increasing in lambda. So the sup is actually the limit when lambda goes to infinity. It describes the behavior of the convex function at infinity. And like I said, you can extend, you can drop the lower boundedness. You can replace that by a condition that in the classical financial utility maximization becomes the so-called reasonable asymptotic elasticity introduced by Krankov and Schachelmeier. That will be enough instead of boundedness. And then if I have a couple of more minutes, I return to this. I think there's two examples. The first is the stochastic control. Here we assume for simplicity that these penalty functions L are bounded from below. And now the linearity condition requires that this set here of states and controls, adapted states and controls, be linear. If you go back to the linear quadratic model, this is automatically satisfied. And in the case of stochastic control, you can write the generalized Bellman recursion in more familiar terms. If you studied dynamic programming in the classical control model, then this should be very familiar to you. Again, we have this recursion, but now it's on the so-called cost-to-go function that we define iteratively from end to the beginning. And again, you get those same kind of optimality conditions for your controls. You also can analyze these kind of things further. You can write things in terms of, in general, you can write conditional expectations in terms of probability kernels if they exist. And from these expressions, you also see that these cost-to-go functions become deterministic if your system matrices are IID over time. So we get many of those classical results from stochastic control from this more abstract dynamic programming approach. The second example is the classical perfectly liquid market model. You look at the utility maximization from terminal wealth. We have two conditions here. One, we are now no longer asking for bounded utility. We can allow for unbounded utilities. The first condition is essentially the reasonable asymptotic elasticity condition that you've seen in many papers since Krankov's and Schachelmeier's introduction. The second condition here, if you don't have portfolio constraints, is exactly the no arbitrage condition. The condition is that this set be linear. If there's no portfolio constraints, it means exactly that if you have a riskless trading strategy, then the payout has to be exactly zero. I would then move to duality, but I guess I don't since I ran out of time and I have a terrible cough, so I finish here.
Thank you, Teemu. Let me see. I don't see questions from the audience, and we are out of time, but there's a little bit of a delay on the YouTube, so maybe someone will post a question. So very impressive program for the entire book.
Oh, thank you. That's the comment I was hoping to.
I hope it sells well, the book.
Thank you. We hope that too.
Yes.
That's the hardest part.
Okay, so with that, maybe we'll close this session and go to the coffee break. And I don't have the link
It's
here
too
for
late
the
for
coffee.
coffee and lunch, but I'll join you with the tea.
That's right, yes. Okay, so talk
All right.
soon.
See you.
Bye, Teemu.
Bye-bye.